Okay, so we would like to welcome today's speaker, Mariano Suárez, who's gonna give us a talk about, titled "Can we hear the Hochschild cohomology of the trivial extension of a Chantal algebra?" So, thank you, Mariano, and you can start whenever you're ready.
Okay, so what I want to do is this is work in progress. So I just want to tell you it's a nice idea and it seems to work. Okay, so what I want to do is to compute the Hochschild cohomology of trivial extensions of gentle algebras. So let me explain what this. Can you see that? Yeah. Okay, so just to set up what I'm going to talk about. So I'm going to take a finite dimensional algebra. This is important. At first, over any field. So we, we take the dual space, the dual vector space. This can be turned into an A by module in the usual way. So that's dA. And then we construct this so-called trivial extension, which is just the direct sum of these two spaces here. So, but we put a multiplication given by that rule. So this is a special case of the singular extensions studied by Hochschild that everybody knows are classified by the second Hochschild cohomology space of the algebra A with values in the A by module dA. So this is a trivial extension because there is no cocycle. It corresponds to the zero element in this vector space. Okay, so that's a trivial extension. Why do we care about this? Well, it's a nice algebra, and but so it plays many roles in the study of rings. So a nice example of what it does is the following. Okay, so this algebra is graded. So you can put this in degree 0 and this in degree 1, so like that. So that gives you a graded algebra. So you can consider the category of graded modules over TA, the trivial extension. So there is a forgetful function. It says you have a graded module, forget the grading, and you get a module over the algebra. So these are small modules. So what the first thing is that the this forgetful functor is a covering. It's a Galois covering with group Z. So I'm not going to explain what that is, but that means that if you are interested in this thing or in this one, whichever you like best, you get to move information from one to the other. Okay, so now that's one thing. Then Happel proved in his book on triangulated categories that the derived category, sorry, the category of graded modules over TA is equivalent as a category to this thing. This algebra A tilde is called so this is the repetitive algebra. So I'm not going to say what it is, but it's a similar construction to A, but infinite dimensional. So graded modules over TA are the same as modules over this repetitive algebra. And then a third step, also done in that book, is that if A has finite global dimension, then we get a description of the derived category of A as the stable category of the category of modules of the repetitive algebra. So this is this category here it's a Frobenius category. So it's something. It's an exact category with certain properties. So when you have a Frobenius category, you can do something that's called stabilizing it. So you get this, and this is one of the big theorems in the book, that you get a description of the derived category of A in concrete terms, if you want, because these things, objects in the stable category, are something that you know. These are simply modules over some algebra, modulo projectives in that case. So this is one way in which TA is useful. If you want to study this and you want to study that, then you can study this. this one is equivalent to this one, and this one is a Galois covering of that one. No? So that's one way in which the trivial extension shows up in nature. Okay? So it has a problem that usually it's a very complicated algebra. One should expect that because of this. No? So the derived category is going to be usually complicated. So for the composition of all these things gives you that TA has to be at least as complicated as the derived category. So that's not good. And one of the reasons why it is a complicated algebra is that the algebra is symmetric. No? So symmetric means, so again, this is just as before. So you have the algebra TA. So this is the TA by module. So this is this by module. So symmetry means that this bimodule and the regular one are isomorphic. So this in particular implies that the algebra is self-symmetric. So it's the regular module on the left and on the right is injective. And usually that means that the algebra is complicated because for an algebra to be symmetric, you need a lot of loops if you want. If you look at the not loops, but cycles. Huh? So you need a lot of round things in the quiver. No? So that usually makes especially computing homology more complicated. No? So that's one of the reasons why it's a complicated algebra. So
Mariano, uh, unrelated question.
yeah.
It a Frobenius algebra or
Yes,
something
it's a
more?
Frobenius algebra. So symmetric is Frobenius and something else.
Frobenius and
Something else.
symmetric Frobenius. Okay. Okay.
So to be Frobenius, you need a bilinear form. If the bilinear form is symmetric, then the algebra is symmetric.
Thank you.
So from this thing, you get a map that looks like this by transposing. So if you have an isomorphism like that, you get a map that does like this. So this is phi of x applied to y. So this is a Frobenius pairing. And moreover, it's symmetric. If you switch the x and the y, you get the same thing. Okay, so these algebras, we know them very much, very well. So one way in which you can see that is that if you have an admissible presentation for A as a admissible, so as a quotient of a quiver, of a path algebra over a quiver, by an admissible idea, then we know how to construct a similar presentation for TA. So I thought this was done a long time ago, but apparently it just appeared in 2022. So this is a paper about something, but there is an appendix here by Elsa Fernandez in which she shows how to construct the quiver and the ideal of relations. No? So it's very easy to show that the vertices of the ordinary quiver are the same as those of A simply because so T of A is A plus dA. This is an nilpotent ideal. So it does not do anything. So modulo the radical, you get the same thing as with A. So that's why the vertices of TA are the same as those of A. Now, the arrows in the quiver of TA are more complicated. You have the arrows of A, and you need to take, so A is an A by module. So you look at it as an A by module. It has a socle, and you need a basis of that, essentially. That corresponds to, so in your quiver, in QA, you're going to have some maximal paths. So these are non-zero paths, which you cannot make longer by multiplying by arrows. So those give you a basis for the ASOC. So you have to reverse them. I don't really care, but we know how to. This is easy to show, and the relations are complicated. So it's not really complicated, but it's not. They are not nice. Okay, so later in 2024. María Andrea Gatica, this is Valeria Hernandez, and Marianez-Platzek, they wrote down the special case for monomial algebra. No? So in the case when the algebra is monomial, it's easier to be more precise, if you want, about the shape of the relation. But it's more or less the same description. Okay? So as in the relations, there are lots of things that look like this. So you have close, so you have paths like that, and then some other paths like this, and the relations, the complicated ones, say that something like if you do something like this and one more time, then you get zero. No? So you have a lot of round relations, which usually make problems when you want to do something with the algebra. Okay, so what I want to do is I want to compute the Hochschild cohomology of these things. Ideally in general, so we would like to do it for an arbitrary algebra, but this is a difficult problem. So it's difficult because, well, to do something for every algebra is not going to work, of course, but even if you look at special cases, it's going to be difficult. And one of the problems that shows up when you want to do this is that you really need to you have to decide what will be an answer. No, because the cohomology is going to be big. So you can say, well, the cohomology is just the homology of this complex, and that's true, but that's useless. So what I want is some very combinatorial description of the cohomology, because I also want the cohomology has a lot of structure. It has a multiplication, it has a Lie bracket, and so on. So I want to be able to compute all that too. And for that, usually you need a very, very concrete, preferably combinatorial description of the cohomology. And one of the problems in doing this for TA is that we don't have a lot of technical tools. So that's true usually for cohomology in general, for Hochschild cohomology in general, but for TA, it's a problem that the cohomology is going to be big and it's a mess. Okay, so that's what I want to do. There is, here it says there are very few technical tools. Well, there is one technical tool that's useful, very useful. So in 2003, Claude Civils, Eduardo Marcos, María Julia Redondo, Andrea have this very nice paper, which says a lot of things, but for us, the only important thing is that there is a spectral sequence. The spectral sequence goes from something to the Hochschild cohomology in general for singular extension, but in our case, so it's a spectral sequence that goes from something to the Hochschild cohomology of A, more or less, of T of A. Yeah? Okay, so the idea of the spectral sequence is not difficult. So you have TA, this is equal to A direct sum dA. This thing here is an ideal. So this is a filtration. And that filtration gives a filtration in the Hochschild complex, the usual big complex that computes Hochschild cohomology, and one works with that. So it works. So it's there. There is a problem. The biggest problem is that we don't have a description for any of the pages. So you have the starting page, which is before you compute any homology, and then for the other pages, you know what they are, but we don't have a concrete description in the sense that we cannot say it is the Tor of something, or we can, no? Because in some way we can, but it does not give us any information. No? So we would like to have a useful, if you want, description of higher pages, and we don't have any description of any page. No? So it's really not very. And of course, if you don't have a description of the things that appear in the spectral sequence, it's even harder to find a description of the differentials. The only differentials that they write down, and I think no one else has done better, are the first, the ones in page A2, which are given by cup products. So it's very nice because the differentials involve something known, but it's useful to construct, for example, long exact sequences and so on, but it's not really something as okay, it's a cup product, so it's zero. No, it doesn't work like that. Okay, so nonetheless, one is able to do things with that. So they do several things in the paper, but the nicest one, I think, and the one that's been most useful later was looking at what happens in very low degrees. So the spectral sequence in degree 0 gives you completely the homology, the cohomology, but that always happens. So in degree 1, so you look at the beginning of the spectral sequence, then you get this description. This is an isomorphism here. So this description for the first cohomology of the trivial extension. No? So this is a very nice decomposition that has the the center of the algebra, so the zero Hochschild cohomology, the first Hochschild homology wave. This is the dual space of H1, and this is something I'm not going to explain what it is, but it's a I'm not going to explain what it is because I don't know. So it's something that they define and it's there, but I don't think anyone really understands what it is. Yeah? So it's some vector space. Very concrete one, but we don't know what it means in terms of, say, the representation theory of anything. Okay, so and how do they get this? Well, they look at the spectral sequence in degree 1, so you always have a very short 5-term exact sequence. So you look at that and you analyze what you have and you get this decomposition. Okay, so one nice thing that you can see immediately for this here should be TA, is that H1 of TA is never 0. Why? Because it contains this part here. This is the center of the algebra that you started with, and that always is at least of dimension 1, because you have the 1, the center in the algebra. Okay, so this is a non-trivial thing. No? The fact that this is not 0, it's not obvious. And it's bigger than the cohomology of because it also contains this one. It's bigger than the cohomology of the algebra that you started with. So, okay, so this is never 0. And as I say, we don't understand this decomposition very well. So what do I mean by that? Because of course, you know it is here, but so H1, for example, has a Lie structure. It's a Lie algebra, so that means that you want to know in what way this decomposition interacts with the bracket, the Gerstenhaber bracket in Lie, or for example, you want to compute cup products. So I know people are working on that, but it's not. Right? It's very worrying that we are not able to do this in degree 1, because doing it in higher degrees is going to be much, much more difficult. Yeah, but okay. So but all this comes from their paper, which is very, very nice. Okay. So I'm doing this in general. It's difficult. It's very difficult, especially if you want to compute. If you say, I want to do an example to see what happens. And so you take a very small algebra A, and when you do the TA, you get the algebra is twice as big, but the relations are complicated. So if you try to do the standard things that you do to compute Hochschild cohomology, it very soon becomes impossible to do anything. So there are not very many examples of this. So I'm really interested in the case in which A is gentle. So what does it mean? I think everybody knows here what a gentle algebra is, but let's just, so this means that the algebra A has a presentation as a quotient of a path algebra modulo an admissible ideal. And okay, so we have a combinatorial condition, the first one that says that at each vertex of the quiver, there are at most 2 arrows coming in and at most 2 arrows coming out. So you could have less, but at most 2 and 2. So the second thing is important, it's useful, is that the ideal can be generated by paths of length 2. So this is a monomial algebra. This is nice because, as I said before, the TA is simpler in some way, simpler to describe when you have a monomial algebra. So this is a monomial algebra. And then there is a combinatorial condition that involves the relations. I'm not going to say what that is because I think everybody knows them, but the important thing is that the condition implies that every time you pick an arrow, then there is an only way to continue it as a path. So you can only go one path in one direction and the same thing backwards. So if you start with this arrow here, then there is a unique maximal path that goes through it. That's not equivalent, that sentence is not equivalent to gentleness, but it's what I need. Okay, so why do I care about these algebras? Well, originally, the first time they showed up is when Ibrahim Assem, Happel, and Andrei Skobronsky started studying. They wrote their two papers in which they study the iterated tilted algebras of type A. You start with a quiver of type A and you start doing tiltings. And what they do is they make a list of all the algebras that you get, and they are all gentle. And then it's not all the gentle algebras, but they get a class, so they give a combinatorial description, and it's very similar to what we have here. There are extra conditions, of course, because we are only looking at special gentle algebras. Then Ibrahim and Skobronsky then did the A tilde case. Okay, and so at some point, people looked at what they had done and they realized that many of the properties of those algebras that in the examples of the iterated tilted of type A tilde, you could generalize for general gentle algebras, and that's the beginning of a very, very long story. So these algebras are very well known. We know all the modules. We understand very well their derived categories to the point that we know all the indecomposable objects, all the triangles, all the morphisms, all the extensions. Well, we know everything. And when I say we know, what I mean is we have extremely painfully explicit descriptions of everything. And in particular, we know their Hochschild cohomology. Yeah, so and that description of Hochschild cohomology that we got in this paper is like I like them. So it's a very explicit thing that allows you to compute then the algebraic structure and the Lie structure and so on, and use that to actually get useful invariants for the algebra coming from the cohomology. That's what we want to do. Okay, so what I want to do, as I said, is then I'm going to try, my objective is try to compute the Hochschild cohomology of the trivial extension now of a gentle algebra. So how can we do that? Well, we have presentations for TA, as I said. So we can write TA as a quotient of a path algebra. And even if the presentations are complicated, they are very efficient. So the fact that we are using the ordinary quiver means we are using a minimal number of generators in some sense. And the ideal that you get from doing this, using the results of ELSA and friends, it's usually not minimal, but it's very small. So you get a very good presentation, and using that, we know how to construct resolutions. To compute Hochschild cohomology, we need bimodule resolutions, and we can do that very efficiently, in some sense, from a good presentation. So, like using, for example, the ideas in the thesis of Sergio Chowi, or somewhere else. Okay, and so you build your good presentation. From that, you build a good resolution, and from that, you write the usual complex that computes Hochschild cohomology, and then it's just linear algebra. So you have to compute kernels and images and quotients. So of course, it does not work like that. It's never just linear algebra, because linear algebra will get you only so far. But the problem here is really that the calculation is too big. So the fact that there are many cycles in the quiver, many cycles in the quiver, that the relations, if you know what this means, you know what it means, is they overlap in many, many ways. So you have a lot of relations, and so the projective resolutions that we get are huge, and it's not going to work. So and it's really not very clear that one is going to get any useful information out of that. Okay, so what do we do? Well, do something different. So as I said, there are not a lot of technical tools to do this. Despite the fact that we know a lot of cohomology and so on, we really don't know a lot of ways to compute it. And that reflects in the fact that we really don't know a lot about cohomology. Okay, so what I'm going to do is something else, so very different. And I'm going to pick an idea that comes from a different context. Okay. So in the 60s, Bertram Kostant computed, this is a very, very famous paper in the annals. He computed the Lie algebra cohomology. So you take, what is it? So you take a semi-simple Lie algebra. From that, you get the so-called nilpotent radical. This is a Lie algebra, and what he did was compute the Lie algebra, the Lie algebra cohomology of the nilpotent radical with, I think, trivial coefficients. So this is important. The people that do Lie theory really like this. It's important for many reasons, but for us, it's only important in how do you do this. So if you try to do, if you take any Lie algebra and write the standard Chevalley-Eilenberg complex to compute its cohomology, okay, so in principle, you only have to do linear algebra. Again, that's not very useful. If you try to do this for but that calculation is usually extremely difficult. So if you try to do this for a nilpotent algebra, it's even worse because nilpotent algebras tend to have zeros all over the place, and that means that your cohomology is going to be big, because your differentials usually have very large kernels. So it's difficult to even compute the Hilbert series of this. It's extremely difficult. So he did. So what did he do? Well, he also took an idea from somewhere else. So the idea comes from Hodge. So in the 30s, Hodge, he was studying the RAM cohomology, and his idea was to use partial differential equations. So you have a manifold. So what he wanted to do is to compute the RAM cohomology of M, not really to compute it, but to understand it. And so what he did was he considered the RAM complex, whose cohomology is the RAM cohomology, and he defined certain differential operators. So this comes with the differential, of course, but he defined certain differential operators which are very similar to the Laplacian equation. So it's like he solved the Laplace equation, the heat equation, but on manifolds and instead of with functions with differential forms. So it's not really important, but he set up a very complicated thing, and it was extremely successful. This is called the Hodge theory. It's very difficult. It's really extremely difficult. For like 30 years, no one really understood if the proofs given by Hodge of what he did were correct or not. So I think it was in the maybe 65 that people finally decided that the theorems were true. Yeah, and not because of the proofs given by Hodge. Hodge gave two completely different set of proofs for his theorems, and both are incorrect. Yeah, but what happened eventually was that it was fixed by other people. No, but everybody recognizes that the idea is really genius. Yeah, so but it's technically extremely difficult. Okay, but we don't really care because that's difficult because of course if you're going to use partial differential equations, it's not going to be easy. Okay, but the key thing for us is the idea. The idea behind Hodge theory is extremely simple and it's very flexible. So we are going to use it in a completely different context. Okay, so what I want to keep from Hodge is the following. So first, I'm going to restrict to working with subfields of the real number. So the cohomology of gentle algebras, you can do this for any field, and it really depends on the field. So for example, when you compute the Hochschild cohomology of a gentle algebra, you see the category, the category of the field. It's either two or not two. That's the first distinction that you see. But when you start looking deeper into the cohomology and you start doing, for example, Lie brackets and so on, you see the category. You can, if I give you the cohomology of an algebra, of a gentle algebra, as an Gerstenhaber algebra, then you can compute the category of the field from that information. So
What do you mean by category of the field?
the characteristic, sorry. The
Ah,
characteristic.
okay.
So when the characteristic is 2, there is a big change. So if the characteristic is not 2, then the vector spaces in cohomology look the same. But if you look at the Lie bracket, for example, then you can actually see the characteristic of the field. Okay, so I'm losing something here. So I'm only going to work with fields of characteristic 0. No, and that's the only thing I'm going to lose, because the cohomology of an algebra does not change when you extend scalars. No? So if you do the calculation over C, over Q, for example, of the rational numbers, then if you extend to any field of characteristic 0, you are just going to extend the field of definition of the complex. No? So what we are doing here is really working over all fields of characteristic 0. Okay, so the idea is, suppose that we have a very little complex like this, and we want to compute the cohomology in the middle, H. So, and these are finite dimensional vector space. No? So what we do is, you put on each of these 3 vector spaces an inner product, any inner product. And okay, so now you have a map. This delta, for example, is a linear map from X to Y. These are 2 inner product spaces. So you can construct the adjoint maps, going backward. And okay, so now you have a diagram that looks like this. So you can do this composition and this composition. So you have 2 maps from Y to Y, and you make the sum of those, and that's that's a linear map from Y to Y. This is called the Hodge Laplace map. Yeah, if you do this this is exactly what Hodge did. He had omega 0 of m, omega 1 of n, and so on. So these are the RAM differentials. So each of these vector spaces, the spaces of differential forms, so suppose you have a Riemannian manifold, so you have a inner product somewhere. So from that inner product, you can define inner products on the spaces of forms. So you can, this is difficult, but it works. You can define adjoints in that case. These are not Hilbert spaces, they're not complete, so it's slightly more complicated, but there are something that's called the adjoint. And what he did was exactly the same. He defined the Laplacian at each degree, so you have a delta here, and so on. These are endomorphisms of each of the RAM spaces. And the only one that's familiar to everybody is this one, the one in degree 0, because this Laplacian is simply the Laplacian. So if the manifold is the vector space, and you have the usual Riemannian structure, then this delta is really the Laplacian of that everybody knows. Okay, so what's the point of this thing, this linear map? Well, so this is our complex that we started with. This is the Laplace. Okay, so the first thing is that this is a self-adjoint linear map. Remember, Y has an inner product, so saying that it is self-adjoint makes sense. And it is positive semi-definite. So everything here is finite dimensional, so being self-adjoint means that we can diagonalize it. And being positive semi-definite means that the eigenvalues that show up when you do that diagonalization are non-negative real numbers. Okay, so this is nice. Then the kernel of delta is, so remember we have our diagram. It looks like this. So you have arrows going in one direction and in the other. So the kernel of delta, which is an endomorphism of Y, like this. Oops. It's really the intersection of the 2 maps. So from Y, you have a map going in this direction and a map going in that direction. The common zeros of that are exactly the elements in the kernel of delta. And in particular, this means that this is contained in the kernel of delta, of D. So you can construct a map. So you take an element in the kernel, you look at it in the kernel of delta, you look at it as an element in the kernel of D, and then you can pass to the quotient. No? So this is, you go to D, and from here to take homology in the middle. Yeah? So this gives you a map that goes from the kernel of delta to the homology of a little complex, and that map is an isomorphism. Okay, so each of these three things is a very difficult theorem when you do it for manifolds. Here it's just linear algebra. Yeah, I never remember how to do this, but it's like a Sudoku, but it works. No, so we call the elements of the kernel of delta harmonic cocycles or cycles, depending on what you're doing. Why? Because in the situation in this situation here, these are precisely the harmonic function. No? The kernel of the Laplacian is the set of harmonic functions. So for example, suppose that M is a compact manifold, then the kernel, the the minimum principle tells you that a harmonic function is constant. No? So that means that the kernel of this map, in the case of a compact manifold, is one-dimensional. No? So what we are saying here is that that kernel is precisely the homology in degree 0 of the map. And since the manifold is connected, because they are always connected, then what you see is that the kernel is exactly the cohomology in degree 0 at least. No? So the big Hodge theorem is that this is true in all dimensions, in all degrees. Okay, so the third part, this thing here, that it tells you is that in every cohomology class in our little complex, there is a unique harmonic representative. No? So this is the difficult part in the differential geometric setting. Okay, here it's just linear algebra. Okay, so this is extremely nice because one of the problems when you compute cohomology is that cohomology classes have many representatives, and usually that brings a lot of problems. In this situation, every cohomology class has a unique representative. And okay, so this is how Bertram Kostant computed cohomology. No, he had the Chevalier-Eilenberg complex for an nilpotent Lie algebra. He chose in some way an inner product on each of the vector spaces. He computed these things, and then you looked at the kernel of that. Yeah? So one nice thing is that usually when you compute cohomology, you have to compute the kernel of a map, but that's not enough because some of the elements are going to be 0 because you're going to go to a quotient. Here, you're looking at the kernel of something, but you don't have to mod out by anything. So the kernel is the homology in this case, because what you do here is you show that this subspace, the kernel of delta, is really a specific complement of the space of boundaries inside the space of cycles. That's how you prove this. So this is good. So another good thing here is that if you have one cycle and you want to know if it's sorry, what I mean is if it's a boundary or not, usually that's complicated. You have to solve an equation. But here, if your boundary is harmonic, then the only way it can be a cycle, a boundary, if it's 0. So you don't have to do anything, supposing that you have harmonic cocycles. Of course, cohomology classes are going to have representatives which are not harmonic. So usually people that you do use this idea, you have to develop some way of starting with any class and modifying the representative so that it becomes harmonic. This is what people that do differential equations do, for example. No, but okay. So what I'm going to do is I'm going to use that idea to compute cohomology. So the point is I'm going to work for the trivial extensions of things. So as we said, this is a symmetric algebra. Let's consider for a little second just any symmetric algebra. So an algebra lambda, which is isomorphic as a bimodule to its dual space, to its dual bimodule. So you take any bimodule projective resolution for lambda, and then you can, so this complex here is what computes cohomology. So you take the home of bimodules to the algebra. Okay, so this complex, well, this is just a definition. No, sorry, since lambda as a bimodule is isomorphic to the A, we can replace this thing here by that one there. Okay, so this complex computes Hochschild cohomology. Now, d lambda is just this vector space with a specific module structure. And now you do from here to here, you do an adjoint formula, and you get this. So, and what did you get? So this complex here is the complex that computes. So this is, if you do homology, that gives you Hochschild homology. So this one computes Hochschild cohomology. Okay, so this is the dual of the complex. Since we are K is a field, so everything commutes with taking cohomology. So we see that the Hochschild cohomology of a symmetric algebra is the dual of the Hochschild homology. So when you deal with symmetric algebras, you can forget about cohomology and work with homology. So why do we do this? Well, because homology is slightly more symmetrical. So if you ever computed Hochschild cohomology, you know you have dual spaces showing up. And in this case, in homology, you just have the algebra. Yeah, okay. So that's why from now on, I'm going to talk about the Hochschild homology. So, of course, suppose that we are very successful and are able to compute the homology of lambda, then you take duals, and that gives you the cohomology. But this thing has an algebraic structure. It has a multiplication and a bracket and so on. So what we are going to get is a dualized description of that. So that's going to give you, instead of having an algebra, you're going to have a coalgebra and so on. So this is not ideal, but well, if it's the only thing you can do, then you're happy. Okay, so I'm going to compute this. So how do we do this? As I said, so you take a gentle algebra, you TA the thing. So I'm going to call E the subalgebra of TA spanned by the vertices. Remember, the vertices of the trivial algebra are the same as the vertices of the algebra. So we know this. And you take you take for P star, I'm going to take the usual standard resolution. So I'm not going to pick any smart bimodule resolution like the Barsdell resolution or anything. So this P is just a bar resolution for the trivial extension. So it's this complex that looks like this. So the only smart thing that I'm doing is since this algebra E is separable, then so what I'm going to do is really, instead of computing the homology of T of A as a K algebra, I'm going to compute the homology of T of A as an E algebra. The two things are isomorphic. Okay, so and how do I do that? I use the bar complex for this, which has these things in each degree. So, and we put the usual Hochschild differentials, and that gives you a bimodule resolution. You tensor it with TA over TA, the enveloping algebra of TA, and you get this complex. So what we want to do is to compute the homology of this. So what I want to do is the homology of this complex. Okay. So a big thing here is that I'm not making any effort to make my complex small. So that's very unusual. Usually, we like to do this sort of thing with very small resolutions because we think with good reason, that smaller complexes make for better calculations. But there is a price you have to pay when you take a minimal resolution. So the problem with the minimal resolution is usually very well adapted to the algebra, and that means that it contains all the information about the combinatorics of your algebra. So here I'm using the bar resolution, which has no information whatsoever about the algebra because the same formulas work for every algebra. So usually we don't use the bar resolution because it is too big. So I don't care. I'm just using the big complex. Okay, so this complex here, so one usually does certain identifications, very, very standard, and you get a complex that looks like this with certain differentials. For example, the first one here, you have tensors like that, and you simply map it to AB minus BA. Yeah, and so on. Okay? So this is the complex whose cohomology I want to compute. Now, A has a basis. No? So this is, since A is a monomial algebra, the most obvious algebra that you basis you can take is the basis of monomials. It's very good because it's a multiplicative basis. Okay, so I'm going to write that B of A. It's a set of non-zero paths in the original algebra. Now, dA, this is the dual space of A, then of course you can talk about the dual basis to the paths. So we have a nice basis. So in that way, you make the union of these two things, you get a basis for the trivial extension. So what I'm going to, so we have a basis for this one. Different color. We have a basis for that one. So what is this space? So that's TA tensor over E of TA. Now remember, TA is A direct sum dA. So this has the basis that we wrote down before are paths. They are like paths and the duals of paths. But all those things have a beginning and an end. So they like begin and end at some point in the quiver. So this vector space, this is not really correct. So here you would have to, what people write like that with a missing term, because these are round terms. So this E here goes from here to here. So these are the correct way to draw these tensors in a circle. Okay, let's forget about that. Okay, so these things have a basis which consists of tensors that look like a basis element here, tensor, a basis element here, in such a way that these two things glue together. So A ends where B begins and B begins where A ends. Okay? So in that way, from this basis of the trivial extension, you get a basis for all these tensor powers. So, okay, so we have a complex with a basis. And now I'm going to do the stupidest thing possible, which is I'm going to choose inner products on these vector spaces so that these bases are orthonormal. So it's like at this point, one has a lot of choices because any choice of inner product works. Of course, if I took a random inner product, this is not going to be of any help. So I'm doing the least imaginative choice. This is not obvious that it's the best one. So
Sorry, Mariano, I have a small doubt about these spaces that you described. So you take first a path, and then you take the dual of paths, and they need to they need to glue them together,
yes,
or it's like this.
so elements of A are really, so I'm taking paths in the quiver.
Yeah.
This is now in dA, so I'm going to use the dual basis of the basis of paths. And I'm going to say, suppose that U is a path. So I'm going to write U star for the dual element. And I'm going to say U star begins where U ends, and that U star ends where U begins. So and now when you write an element in one of these tensor powers, they look like this. For example, in degree 2. So the condition here is that, what is it? That this path ends where this one begins, this ends where this one begins, and this one ends where this one begins. Yeah?
Okay. Yeah.
So, but some of them are paths and some of them are dual paths. So
okay. Okay.
If you make a little picture of this looks like U1, for example, then U2 going in the other direction, for example, if it's dual, and this one looks like that. So if you know about gentle algebras, and you know about gentle algebras, then this is the sort of thing that you count when you do a AAG invariance, for example. Some of these. So I want to converge to that, of course.
Yeah, of course.
Okay, so I declare that those basis elements are orthonormal. So that's an inner product. What I was saying is that, for example, if you start with a gentle algebra, so one way you can get a gentle algebra is from a triangulation of a surface. So when you have a triangulation of a surface, people study this a lot. So there are very important because they're useful other inner products on the space of paths in a triangulation of a surface that take into account the angles between. So you make a realization of the triangulation using geodesics. Also, you pick a harmonic, so a conformal structure on the surface. Say, for example, you pick a Riemannian metric of constant curvature -1, and so you can always draw the triangulation that gives your quiver using geodesics and triangles. So the real geodesic triangles, and you can measure angles. No? So there is an inner product in the space of paths in a triangulation that takes into account those angles. And that is very well defined because it is something that people study. It's more or less canonical. And from that, you can get a different inner product on my vector spaces. No? So there are there are finer ways to choose inner products. Yeah? Well, for now, I'm just taking the stupid one. Okay, so once you choose inner products, then as I said, you can compute explicitly the adjoints of the differentials. Using the formula of Hodge, you can compute the Laplacians at each degree. And then you just have to compute the kernel of those maps. So that's, of course, not very easy. So I'm not going to give you the complete formulas because I have the formulas for the Laplacian and they are useful, but I have not finished the calculation. Yeah, so I don't know if you wanted to hear me tell you what the cohomology was. I don't know, but okay, so let me explain you how far I got. No, so let's do the simplest example, which is in degree 0. Why is degree 0 simpler? Because this Laplacian has only one term. Since you have a 0 here, the Laplacian in degree 0 is just take the adjoint here and come back using the differential. So that's the easiest one to compute. So let me explain what this delta 0 map does. So TA, as we said, has A inside and dA. So the paths in this vector space, we have the paths, and here we have the duals of the dual basis of path. So we have this is a description, a very concrete description of delta 0. So if you have a path, so this B of A means the basis of A. So if you have a path, and means a non-zero path in A that has length at most 1, then the Laplacian kills it. That's very easy. So what does it do with longer paths? Well, if you have a longer path, then so the Laplacian of u is just this number, which depends on the length, times u. So all the paths are eigenvectors. Remember that this delta 0 is a self-adjoint linear map. So it is diagonalizable with it's also semi-definite positive, so its eigenvalues are non-negative. So this is in the kernel, and this number is positive because this only works for u larger than 2. Okay, so what happens if you do this for an element in the dual basis? So the Laplacian of a dual path. So if the length is positive of the path, then you get this mess here. So this is just the dual element with which we started. And what is this? So remember, so here we have u is some path. This is u. So remember that this is a gentle algebra. So once you choose an arrow or a path of positive length, there is a unique way of extending it in both directions. So this u tilde, or u breve, that's called a breve, it's the maximal extension of the path. So this difference here is how many arrows you can add to u. So when is this 0? Well, it's going to be 0 if you cannot add any arrows to u. That means that u is a maximal path. Okay, so it's 2. There are 2 everywhere. So if you take a path of positive length, then delta of the dual element is just how many arrows you can add to it times the same thing. Again, these are eigenvectors. And the complicated part is this one. It's very annoying that this is complicated, but this is for the vertices. So this is what should be easy. But it isn't. It's the most complicated part. So if you have here the dual element corresponding to a vertex in the quiver, then you get this sum. So let me explain what do I mean by that. What are these numbers? This is, you take, so if U is equal to I star, the dual of a vertex, you get this thing here, which is a linear combination of duals of vertices. So this means that the Laplacian preserves the subspace of dual vertices with these coefficients. So let me explain what those coefficients are. So this is the formula. What is all this? Okay, so we have your Q and your I. From that, I'm going to construct a new graph, because why not? This is going to be gamma. This is called I call it the reachability graph. It's a strange thing. So the vertices of gamma are just the vertices of Q. So you have the same vertices. They are really the dual vertices, but it doesn't matter. And so I'm going to connect two vertices with an edge, so I from J, when there is a path going from I to J in one or the other direction, a non-zero path that connects one of the two. So this is going to be a graph which is not directed. Because of this, I don't really care in which direction the paths go. And it's going to be simple because I'm not going to put any loops, and there are not going to be any parallel arrows, and it's going to be edge weighted. That means every edge is going to have a number. And the number, so if suppose that you have I and J, and there is some path going from one to the other, so I'm going to put here a number, Wij, which is the number of paths that connect I and J in both directions. Something. Okay, so this is not a graph, it's a graph with numbers on the arrows, they are not arrows on the edges. Okay, so, and then I define the degree of a vertex is simply the sum of all, so you have I, from there you get some arrow, some edges that connect it. I'm going to sum all the weights of the arrows, of the edges that come out of I, and these Mij's are these numbers. In the diagonal, you have the degrees, and in the outside of the diagonal, you have minus the weights. So this is the numbers, these are the numbers that appear in this formula. Okay, so this looks very mysterious, but it's not very mysterious. So when you have a matrix gamma, any graph gamma, from that.
Sorry, one quick question, Mariano.
Yeah.
These Wij's, do you count the paths somehow double? Like if you have a path in one direction, it's also a path the other direction. So do you count it twice or just once?
No, twice.
Okay.
You just count all the paths that go from one to the other in both directions.
Okay, so it's always an even number. It's always
that's why you see here you have a lot of twos. All those twos comes from the fact that this does not really care about that.
All right, thanks.
Okay, so what is this matrix Mij? Well, when you have a graph, an unoriented simple graph, like we said before, there is a very standard construction. Again, the people in graph theory know about Hodge, so they reinvented the Laplacian of a graph. So there is something called the Laplacian matrix of the graph gamma. And this is what people that do spectral graph theory study. So people that do, this is very fashionable now. This is what people do in the ChatGPT and do. It's a very cool thing today. Okay, so this is usually done for graphs, but if you have a weighted graph, like our graph, then there is also something called the Laplacian matrix of a weighted graph, and this is precisely it. So this matrix A is just the Laplace matrix of the weighted graph gamma. So the good thing about the Laplacian theory of this is the spectral theory of graphs, is that people know a lot about that. So in this case, so since the quiver Q is connected, then of course gamma is connected. And from that, the Laplace matrix of gamma, one can show that has corank 1. So that is an almost maximal rank. And the kernel is spanned by the constant vector 1. And it's also positive, definite, and symmetric. So that means that if we go back to our formula, so what do we do here? So here it says that delta acts diagonally, that's almost diagonally, on our basis. On paths, it acts diagonally, truthfully, and on duals of positive paths also diagonally. So we have a basis of eigenvectors for that part of TA. And for this little subspace of vertices, of dual vertices, we have, it acts in a complicated way because it depends on this reachability graph, but the matrix that describes that is very well known. It's something that people really, really know. So from that, you get this. So now how do I compute the kernel? Because remember, the zero Hochschild homology is just the kernel of this map. So this part of the basis is they are eigenvectors. So it's just a matter of looking at which of these vectors have 0 as an eigenvalue. So of course, these ones have 0 as an eigenvalue, and none of these have 0 as an eigenvalue because here the length of U is at least 2, so this number is strictly positive. As I said, this is going to be 0 if and only if this coefficient is 0, and that happens when U is maximal, because in that case you cannot add any arrows. And then you have this part which is more complicated. But the kernel of this part is precisely this thing. This is what people in spectral graph theory found. So if you write what that means that the kernel of these maps is 0, is the complex in degree 0. So you have these little these tensors like this with a round thing is because they are round. The correct way of drawing them is in a circle. So you have paths that are loops and have length at most 1. Then you have the duals of maximal paths that are round also, and then this element which corresponds to this vector. This is just a translation. I just looked at the vectors that have 0 eigenvalue and the kernel of the Laplacian of the graph. Of course, this is, so if you look at what you have is this. So we already know this. The center of this is a trivial calculation. The center of the trivial extension is the direct sum of the center of the algebra plus the dual of H0. So what's the center of the algebra? Well, the center of the algebra is spanned by 1. This is the 1 on the algebra. The maximal paths, because the maximal paths, when you multiply them by arrows, you get 0, so they are central. So this part here and this part are the center of the algebra. And this thing here, these are loops that are central. So this is that part. Sorry, not central. This condition, if you write down what it means that they are not commutators. So this is this part. You got a dual somewhere. It's okay. But so if you look at what you got, and actually this decomposition, which is very natural, jumps at you when you do this calculation in this way, because the elements in this basis are of 2 types. If you look at one type, you get one of the summands. If you look at the other ones, they're in the other summand. Okay, so this is not going to get me a Fields medal, but it's nice. Okay, so one thing that happens is that we were able to compute the spectrum of the graph so not only we found the kernel of delta 0, but looking at this picture, we know how to compute the eigenvalues. Remember that delta 0 is it's diagonalized, it's a self-adjoint, semi-definite positive linear map. So it has a spectrum, the set of its eigenvalues are real numbers and so on. So, and we can look at them. So all this part gives you some eigenvalues, 0, these numbers and these numbers that have to do with the length of paths. And then you have this part. So what are the eigenvalues of this part? Well, this is precisely the set of eigenvalues you get from that are the two times the eigenvalues of the graph. So when you have a weighted graph, as I said, it has an associated Laplace matrix, and that matrix has eigenvalues, and this is called the spectrum of the graph. So the spectrum of delta 0 is this set of numbers. So it has to do with lengths of things in the quiver, non-zero paths in the quiver, and 2 times, this 2 is annoying. You see here the 2 and the 2, so we should cancel the 2 because it's annoying. But so you have lengths of things and the spectrum of the reachability graph. So it's a very natural question. This is usually, here I wrote it as a set, but it's really a multiset. no? Because each of these eigenvalues has a multiplicity. No? For example, the multiplicity of 0 as an eigenvalue is precisely the dimension of H here, the dimension of the kernel. No? So it's a very natural question if the other numbers mean something in terms of the representation theory of the algebra. No? So, and this is just at the level of the center. No? So this is where the title of the question comes. No? Because in the original setup of Hodge, so you have a manifold and you pick a Riemannian matrix, and from that you find what we are doing here is looking at the eigenvalues of the Laplacian on the Riemannian manifold. And those are so the idea is that if the manifold vibrates, the eigenvalues are the frequencies of the natural frequencies of the thing. No? So for example, if your manifold is a disk, then you look at it like a drum, and it vibrates in certain frequencies, and the eigenvalues are precisely the frequencies at which the drum vibrates. No? So there is a very classical question by Cox that can you hear the shape of a drum? No? What does that mean? Is that if you know the eigenvalues of a drum, for example, of a manifold, can you tell me what the manifold was? Well, the answer is no. Yes, and sometimes yes, sometimes no, but it's something, it's a very interesting problem. So you have people in, for example, Lauret, what's his name?
Yeah, Emilio.
Emilio, works on
Yeah.
that. No, so Miatello, what they do, they live out of, they make a living out of finding pairs of manifolds that have Laplacians with the same eigenvalue. No, so that's a very for reasons, but that means that you cannot hear the shape of a manifold. No, so here is the same thing. If this set is the set of frequencies at which our algebra is oscillating. So what can you tell me about the algebra if you only hear it? Yeah, so if you hear at the multiplicity of 0, that usually means that the intensity of 0, if you want, then you can tell me the center of the dimension of the center, for example. Yeah, so, okay. So this is what we said. So the multiplicity of 0 as an eigenvalue is precisely that. And this usually works. So usually there are a lot of situations in which people want to compute the homology of something, so they write it as a kernel of a Laplacian thing, and then it turns out that all the eigenvalues, not just the kernel of the Laplacian, gives you information about something. So this is like you have an invariant. I don't know what it measures. Okay. So of course here this part we understand very well. These are, as I said, these are lengths of paths, non-zero paths in the algebra. So that has a very obvious interpretation. This thing here is more complicated. It has to do with the spectrum of this reachability class, the graph. But for example, one thing you can do is you can take the spectral radius of delta Z. So this is the maximum of the eigenvalues. And this is the eigenvalues are real numbers, so this is really the maximal eigenvalue. And usually that's like a measure of how complicated the spectrum is. Of course, it's not going to be 0, so the maximal eigenvalue is exactly in the opposite direction as 0. So it's far away from cohomology, but it's a very natural thing to study. Okay, so if you want to play a little, it's a very easy to compute. If you have an algebra, you compute this thing, it's very easy to compute, and try to see if these numbers mean something. Okay, so what happens in higher degrees? So this is, as I said, all this is in degree 0. So what I have formulas for the Laplacian in all degrees. I have, except degree 1. Degree 1 is slightly more complicated. I had a formula and it turned out to be not right, but just insistence. Degree 1, if you know gentle algebras, it tends to be the most feisty degree. Okay, so what we do here, notice, so
Pero
yes.
one is in the paper with Christian and Sibille for trivial extensions, the Lie algebra structure that we have there.
Yes, I know, but and when with the correct formula, I can get the same formula. But I'm just trying. I want to, because I'm not really interested in the low degrees because we know that. And so a very nice thing of this is that you can do the calculation in degree 15 without knowing any of the other degrees. Yeah, so it's like this calculation in the center. We know this. So it's not new. So what is different is that I'm doing the calculation in a very different way.
But I wanted to check that it was the same result.
I can't hear you.
No, there's a way to check that in degree 1, you know.
Yes. No, but what I mean is the formulas for the Laplace operator. Because usually the one problem with this is that when you compute cohomology, you simply ignore everything that's not a cocycle. But the eigenvalues of the deltas, for example, really depend on everything, not just the cocycles. So one nice thing, so I should have said this before. So I did this calculation for gentle algebras. So if you take the bar complex for a gentle algebra, not the trivial extension, and you put more or less the same inner product so that paths are orthonormal, then again, you have a Laplace Hodge operator, and the kernel of that is precisely the homology or the cohomology of the gentle algebra. And a very nice thing is that the basis elements that we found in our paper, Andrea, are the harmonic representatives. So it's like our representatives are natural in the sense that we chose them because it's the first ones that you find, but it's really the natural generator. Yeah, but that's a much easier calculation. Yeah? So here the dual make it difficult. Okay, so just let me explain a little bit what happens. So when you do this calculation in higher degrees, it's more complicated. It's really pages of calculation, but so you take each of the differentials and you write it simplicially. As usual, this is not really simplicial because the last D is the one that goes back, if you know what I mean. And so these are the terms in the Hochschild differential in homology, and we call delta I the transpose of each of the terms. No? So there is a lot of identities between these things, but you get a formula for the Laplace operator in degree n, which looks like this. No? So it has this part. This is simple. This is more complicated. And then you have this extra term. This term, if you see here, you have things that have a 0 and things that have an n or an n+1. These are the complicated one, but they are outside simply because they are different, but those are the terms that involve jumping the whole tensor. Okay, so the thing is that this is a massive simplification. Yeah? So if you write the formula for delta t, you get a huge thing, but a lot of those terms cancel. So what you only get this part. Okay, so and the nice thing is that each of these three terms has a concrete concrete description, very much in the spirit of these formulas. For example, here you say delta u of u tilde is equal to 2 times the number of arrows you can add to it times the thing you started with. So this number is a very combinatorial thing, okay, so that you can count. So here it's the same thing. So for example, let's start which one? So this term here, it can be written like this. So that thing, that part of the map is equal to this. What is this? Okay. So suppose you have one of my basis elements in the trivial extension. This means that it's not a path. So it's in the radical. Okay, so this nu of u is just the number of ways in which you can factor it as a product of basis elements. It's something you can count. And then remember, this is defined on elements in the basis of the algebra, but our complex has things that look like this. So tensor products of those things. So what this nu I means, just take a basis element here, apply this nu at some point, the position I, and that gives you a number, and multiply u by that. So this is a diagonalizable linear map on this vector space that counts the number of factorizations of what's in one of the places. So this is counting things. And then this epsilon is just a simpler thing. So we have one of these tensors there. And this epsilon just kills it if this one can be a vertex or not. So it kills it if it's not a vertex, and it does nothing if it is a vertex. So again, this is a very combinatorial thing. I give you one of these tensors. It's very easy to compute nu I of that. You just have to count something, and the epsilon is even easier. So the first term in this operator is just that. So you give it a basis element, so you get 2 times that element minus 2 epsilon, which is this thing with the vertices, and this term, which is just multiplying by that. So this is a diagonalizable element map, because each of these summons takes a basis element and multiplies it by a number that you can describe.
Mariano,
Yep.
I think I don't understand something that the nu is something different than the length of the path, because I am thinking about
Yes, because remember that lambda is a direct sum TA.
Yes.
So when you multiply two things in A, so you have a path. If you have a path and you look at factorizations of the path as a product of path, then it's the length minus 1.
But you have more things.
But if you have something in the dual, then that a factorization, so let's make a picture. So for example, you have this path. If you can extend it in some way, then you get this longer path, V, say, and call the rest omega. Then U is equal to, I never remember in which direction, but it's V times U star. So when you multiply in the original algebra, the paths concatenate with each other. But when you multiply with elements, an element in the algebra with an element in the dual algebra, you shorten things.
Now my question is that finite?
Yes, because this is just I'm looking at, so I'm taking a basis element and I'm counting in how many ways I can write it as a product of elements in the basis. So this factorization has A and B belonging to the basis. The basis is finite, so nu of I is a finite number. Okay?
Thank you.
Okay, so the details are not very important, but the important thing is that this part of the delta n is a diagonalizable map. It's diagonalizable in the basis, in the easy basis, and the eigenvalues of that part I know very well. Yeah? And the same thing happens with the other one. For example, here, so this is the second term, this one. Oops, this term. So look, that thing here is equal to 2 times epsilon, the same epsilon as before, that looks at one of the tensors and tells you if it is a vertex or not, plus this thing. So what is this? Well, that's one example. So suppose you have two elements in the basis, U and V, that this condition here means that one ends where the other one starts. Okay, so what is this? It's a sum. So what is this one? Well, so you start with U and V, you multiply it, and then you look at ways in which you can demultiply it using elements of the basis. So you multiply it in one way, and you want to find other ways to construct it multiplying basis elements. No? So again, and this is similar. This one, I'm looking at factorizations of U as a product of two things. And here I'm looking at factorizations of V as a product of two things. So this is complicated, and this is delta or nabla, and this is nabla I means usually you have a long tensor and you take two of the factors and you apply the nabla in that place. So this index I here tells you where you are going to apply this operator delta, nabla. Okay? So again, this is something that you count. This formula looks complicated, but it's really something that's related to the graph that we said before, the reachability graph that I have. Okay, so this term counts factorizations. This one counts rearrangements. It counts, you have two things, you multiply it, and you try to write it in a different way. And how many ways you can do that. And this one is a combination of those things, but with things in the endpoint. So the first factor in the tensor product and the last factor. Yes. I omit that part. Okay, so what does it mean? It means that, well, that one can actually write explicit formulas for the Laplace operators. They are very, very explicit. So, and the good thing is that if you give me one element, it's very easy to compute the value of the Laplace. So you can check, for example, if a cycle is harmonic. And it's something that you can do cycle by cycle. Usually, when you compute cohomology or homology, you have to do it the whole thing. Because to decide if something is a boundary, for example, you need to know if it's not in the image of the differential. So you have to do it all at the same time. Here, you take a cycle, and if you know it is in the kernel of delta, then it is a non-zero. You don't have to do anything else. It's a non-zero homology class. And it's easy to compute. What do I mean by that? Is that, for example, you have TA, no? So an element here, some degree. For example, the typical thing is, suppose that you have a tensor which is just one arrow in each factor, and such that you have relations, zero relations in those arrows all around. That's a typical thing that you find when you do the Hochschild cohomology of a gentle algebra, for example. So it's trivial to show that that's in the kernel of delta, because arrows, remember, for example, the first term here, this one, counted ways of factorizing one of the things in the tensor. For example, you take one of these arrows and you try to write it as a product of two things. And it's impossible simply because it's an arrow. And the other term counts something else, and it's obvious that there are no things, so the eigenvalue there is also zero. So you look at this element and it's immediate that you get a cycle. And since it's in the kernel of delta n, it leads to cohomology. So you have a non-zero cohomology class. So one thing you can do with this is show that all the cohomology spaces are non-zero, for example. Simply because you don't have to compute the cohomology. You just say, okay, I find these elements, and these are in the kernel of delta n and in all degrees. So all the cohomology spaces are non-zero. Something like we did before with the here. So how did they prove that this is not zero? Well, as I said, they just look at this. This is not zero because there is an element there, the one. So this is not zero. Okay, and how you do that? Well, you somehow find an element and you somehow prove that it's not a coboundary. So exactly the same thing here, but the thing is, since these deltas, these Laplace Hodge Laplace operators are very combinatorial, you think a little bit and you can find elements in your algebra that, you can find elements in tensor powers of your algebra that give you non-zero classes in cohomology, for example. Okay, so of course it's complicated, no? So if you have a graph, it's not obvious how when you found all of them. That's at the point time. I have a lot of cocycles, so I found a lot of harmonic elements in each degree. Well, they are correct. They are related to what you expect. They are complete cycles and co-complete cycles and that sort of thing. It's interesting. So when you compute Hochschild, Hochschild homology of gentle algebras, you get things. If you read our paper, and of course all of you read our paper, then you know that they are related with cycles in the graph that have no relations or that have all the possible relations. Here, as we mentioned, we have the possibility of having paths that go in a direction and then duals of paths that go in the other direction. So you get some things that look like this. So elements in the dual, elements in the algebra, and so on. For example, one thing you can do is, if you remember the paper of the Abela Laminos and guys, they define these things that the invariants count. So these are sequences of some things that satisfy a lot of relations. It's very easy to show that those elements give elements in the kernel of delta. So those things, each of the things that they count, give you a basis element in the Hochschild cohomology of the trivial extension. This is what it should happen, of course, but if you know what happens for gentle algebras, then this is what you wanted to prove. But the problem is that I don't know if I have all of them. So using that, you can construct some elements in the kernel. I don't know if I have all of them. Okay, and so it's very nice because the definition, I don't know if you remember that definition. I don't, I never remember, but these things that the conditions that they put on these sequences that they count turn out to be that some of these coefficients are zero. So remember, each of these functions here and before, in all the terms, they count some things. And the conditions that define the set of invariants that they define means that there is no way to do something. That there is no way to do something is the same thing as the number of ways of doing something is zero. And those numbers, those counting, are precisely the eigenvalues of these little pieces that appear here. So this is like an explanation of why you would define the things that they are counting. Yeah? Okay. So that's one thing. And so as I say, for me, the nicest thing so far is that you are able. So remember, Andrea, that paper, I think it's you with Michelin, in which you show that if you have, I think it was a complete intersection, then the cohomology is not zero or something like that. And that was done by, okay, I have no idea what the cohomology is, but I have this cocycle.
Yes.
And I have some way of showing that this cocycle is not a coboundary, so the cohomology space is not zero. This is something that here you can do it for free.
This is the idea that you had a long time ago.
Yeah. It actually, the problem is that it's really very, I'm not showing you the calculations because they are imbalanced. So it's really counting, the formulas for these things are very annoying, but it actually seems to work. So one thing that's interesting is that when you do for example, in the case of manifolds, so every homology class has a representative. Now, suppose that you have two harmonic representatives, so zeros of the Laplace operator, and you do the wedge product. Usually, it is not true that the product is harmonic. No? So the class of manifolds for which that works is very special. They are the formal manifolds. For example, it works if you have a Kaehler manifold. And so those are very, because the next step would be compute, say, for example, the cup product. No, but here the same thing happens. It's not true that the cup product of two harmonic cocycles is harmonic. So this sort of picks a special class of algebras, which are the ones for which that works. No, in the geometric case, and even in the case of graphs, that formality condition is actually very important. So maybe this gives some information about the algebra here. No, so the nicest thing for me is that it gives you a lot of numbers. No? So you take more or less canonically inner product on these vector spaces, and then you have the spectrum of these endomap, these linear maps, and that's of course canonically attached to the algebra. So it's a very reasonable question if these numbers mean something. In the other situations in which you do this, they very much mean something. They're important numbers. So it's a good guess that, for example, even in degree zero, this number, where was it? So this set, or at least the maximum of that set, it should mean something. So the minimum is always zero. No, the fact that it's always zero is more or less the same thing that the center is non-trivial. No? So the minimal eigenvalue is zero, that we know. And again, that's of course a trivial thing. The zero is not trivial. Okay.
I think I would like, not today, but because it's almost 10 p.m. here, but maybe you can tell us what do you obtain in examples? I would like very much to see.
Yeah, so it's just a matter of so you can do it in examples like, for example, you take a cycle and you truncate it with all that sort of thing. The example I would like to do, but I don't know how to, is you start with a surface. For example, with a triangulation of a surface, so that trying to do what Sibile did in the last chapter of our paper. So try to see what the harmonic things are in terms of geometry, because otherwise it's not really clear. No. So far it's more concrete than saying the homology is the homology, but less concrete than saying the elements that you find are these ones. So it's something in the middle. So I can do that thing with proving that there are non-zero elements, for example. That's not difficult.
Okay.
Well, thank you, Mariano. Are there any questions?
No, pero yo igual quería decir, yo me vengo guardando. Just the last question, the one I didn't forget. Is there any possibility to take maybe another inner product, not as canonical as this one, but maybe, I don't know, would that change which cocycles are the harmonic ones?
Yeah, so if you change the
other ones.
Yes, that's my worst. I am almost sure that it should be like that. So these inner products that I'm picking are not very significant. So why these inner products? Because the algebra has many presentations as a gentle algebra usually. I mean, if you have there is a theorem that says that if you have a gentle algebra, then all presentations as a gentle algebra are the same. You always have the same quiver and the same relation. But of course, if you have an algebra, it has a non-trivial automorphism group. So if you conjugate everything by an automorphism, you're going to get different inner products. So a reasonable inner product should be invariant under the automorphism of the group of the algebra. And this one is not. So everybody knows examples of monomial algebras that you do some automorphism and you get a non-monomial path. These are I learned this from Patrick Lemaire, for example. So there are other inner products. So for the biggest candidate, I think, is this. It's called the Whitney inner product. So this is an inner product that people use when you have a triangulation on a surface. So when you have a triangulation on a surface, there are certain canonically defined angles between the segments. And this inner product the problem is that it's very weird. So you more or less you say that the inner product between two arrows is going to be the arc tangent of the angle formed by those two angles. Oh, of course, you can draw the triangles in many ways, but you do this calculation of the angle using a specific canonical inner. So you draw your surface on for this you need a graph that you make a picture on a surface of genus at least 2. So in that case, there is a more or less canonical Riemannian a conformal structure. So there is a well-defined angle between the segments in a geodesic triangulation. So that gives you an invariant angle. That's something that's well defined for sufficiently big graphs. And that's a very canonical inner product. That's really well defined because remember, for example, the, the Gentile algebra corresponds to, because of the theory of Sibile and friends, to a triangulation on a surface and so on. So from that, you get some angles. From those angles, you get an inner product. So the problem is that that's a much more complicated inner product, but it changes the eigenvalues. For example, if you do that, then here the spectrum of delta zero is going to be different because now it's going to be depending on those angles. Of course, the multiplicity of zero has to be the same because the multiplicity of zero is the dimension of the center of the trivial extension, but the other ones are going to change, probably. Yeah, so I spent quite a long time trying to answer your question. So the basic thing is if you have this situation, so you pick inner products on the three spaces, that gives you this, and then you have the Hodge map. So your question more or less says, in what way do the eigenvalues of delta change when you change the eigenvalues, the inner products? And it seems that people don't know.
But also you can change the Gentle algebra and get the same trivial extension.
Yes, but so when you start with a Gentle algebra, you go to the trivial extension and you cut it back to a Gentle algebra. What you do is you cut some cycles. No? So the basis that you get is the same one as before. So that operation more or less preserves the path.
Okay.
So it's a really purely combinatorial thing that happens on paths. So while the complex is going to be different, the inner products that you're going to get here are the same when you do that. That's nice. So when you have a gentle algebra, the automorphism group of the algebra has a big part, which is a big torus that corresponds to automorphisms that multiply arrows by scalars. These are diagonalizable automorphisms. And the things that are invariant under those automorphisms are precisely the things that preserve the paths, if you want. That operation that you start with a gentle algebra, you go to the trivial extension and you go down to a different gentle algebra, preserves the path. So this is a torus invariant thing, and that preserves the inner product that I'm using. But the problem is that, for example, if you take an element in the radical, you can do the radical of the algebra, then you can do a change of basis that corresponds to doing the exponential of that thing. So that maps arrows to things that are an arrows plus a path. And in that way, you get different presentations, and in that way, you get very different inner products at first when you look at them naively. So I really don't. Yeah, I find it very distressing that people that study this don't know how the Laplace map changes when you change the inner product. It's the first thing I would have looked. No, so these people that do like this are, for example, Jonathan Barmack. The people that move around that part of combinatorics. So they have a simplicial complex, so they want to know something about the homology of the simplicial complex. So they do Hodge theory, discrete Hodge theory, they call it. So it's something, but they do the discrete Morse theory. But along the way, they do exactly this. They put inner products on the space of simplices, of simplicial chains, and use it to compute the homology as the kernel of delta, but they have a very good reason not to change the inner product because they have the simplices. For them, the simplices are something very concrete. You cannot change the simplices. But for an algebra, you can change the percentage. So that I really don't know. And it's very annoying because all these calculations are very long. So it would be extremely annoying to find that the correct inner product to do this is not the obvious one.
Are there any more questions?
I have a question. Yeah, so in that very same slide that you had before, you were using subfields of R.
Yeah.
This is
So,
in order to have the inner product have the nice properties that you would like, or what's the...
so you need it to be, so you need a notion of positivity.
Right.
So probably
Right.
you can do this for in some extra generality, say for a quadratic extension satisfying some condition, but I don't think it's going to be of any use.
Right.
So restricting to fields of R does not really restrict a lot. Okay? What you're saying is that your field is characteristic zero.
Yes.
So because if you compute the cohomology over any subfield of R, then you are really doing it over Q because the gentle algebra has no coefficients. And then since Q is contained in every field of characteristic zero, then what you are really doing is doing the calculation over fields of characteristic zero. But
so you also getting the complex numbers, right? Because I mean the question came because in general when you do like finite dimensional algebras, you always want to have it on an algebraically closed field and so on. And
but Hochschild cohomology is really does not care. So if you have a real algebra and you compute the Hochschild cohomology as a real algebra, the cohomology of the complex version is just the tensor product over C.
Right. You complexify the vector space.
No, that's why you can go all the way to the rational numbers. Because in the presentation of the gentle algebra, there are no coefficients. So you can work over Z if you want. Over Z is much more complicated because then you cannot divide. But so
yeah.
And that's going to be difficult. Yeah. But this is really no restriction if you are only interested in fields of characteristic zero. Of course, we are not only fields of characteristic zero, but it's a good step.
Yeah. So so the Hochschild cohomology doesn't change that much. But you know how much it changes and
it changes in a very
base fields.
So you just extend scalars.
No quieres interrumpir. Tengo que ir ahora, porque tengo que hablar con Nicolás, así que lo saludo.
Okay. Bye. Yeah, by the way, Ivans wrote to me saying that he needed to go as well.
Okay.
He had a meeting at 11.
Do we have any further questions?
So a very naive question. I mean, and I know that for gentle algebras, you have a lot of combinatorics and the possibility of do a lot of concrete calculations. So what happens for more general algebras? I mean, can you develop the theory nevertheless? I mean, here is there.
No. So because it really depends a lot. For example, that the long paper in which we did the complete calculation it's only possible because the algebras are gentle.
Right. Yeah.
So it gives you so much combinatorial constraints that you are able to write down basis elements and so on. In general, that's impossible.
But in order to, so you really need the gentleness in order to define these Hodge last maps and
no. For this, the whole theory works for absolutely any algebra. So it works on a complex.
That was what I mean.
So if you have any complex, then you put in the finite dimensional complex
you put the inner product and
it works. It always works. And people do it in a lot of situations. For example, when you have a simplicial complex, when you have a graph, you have people that do Markov chains, a lot of different situations in which they do the same.
Right.
Usually they have their inner products come from somewhere. So they have an
Right.
inner product, so they don't have to choose anything. Here it's somewhat arbitrary. There is really.
Yes.
But
Yes.
sorry, it's arbitrary.
Okay.
You get information from the paths, for example.
Yes. But this inner product that I mentioned, that the one that measures the angles, also gives you information. So if you look at people that work on that, they tell you that that's the correct inner product. So of course it's
Right.
correct
Yeah.
for what they do. Other people that work on this are people that do persistent homology. So they do the same Hodge thing, and in their cases they choose inner products that work well with what they are doing. So it's a very flexible idea. So it's used every time you want to compute the homology of something. You can do this. We did this, for example, in Fernando Martin's thesis. He was computing the homology of combinatorial somethings, and one way to do that was choose certain inner products and compute these maps delta. And usually what you expect to happen is that you have this delta, and it turns out that it comes from it is the Laplace matrix of some graph that someone already studied.
Mm.
And so they tell you what the eigenvalues are, the multiplicity, so you don't have to do anything. So that happens more often than you think, because people spend a really long time looking at these linear maps. And that happened with Fernando. So it was some very complicated thing, but it turned out to be already done. So we just looked at the multiplicity of 0 in the table of the spectrum, and that was the dimension of the cohomology that we wanted.
Right.
So those are very structured situations. Here you have any gentle algebra. So one reasonable sense to make a gentle algebra something you can find in nature is get it from surface, of course.
Yeah.
And that's annoying because the natural linear product that people put on that usually involves the angles, and I'm not using that.
Right. Yeah.
But
Okay.
But as Javi said, I'm getting sensible numbers. So in degree 0, the eigenvalues are lengths of paths. And that's something you can actually look.
Measure.
But for example, the length of paths is not a derived invariant.
No.
So
All right.
So that means that that number is not really. I'm using the Hochschild cohomology to define it. So anything that you define using Hochschild cohomology is going to be derived invariant. And that means that that particular number is not derived invariant. But it is Morita invariant.
Yeah.
For stupid reasons, because the quiver is a Morita matrix. But
yeah. Okay.
Are there any more questions? All right. Well,
a last one.
Yeah.
Mariano, do you think about these things as music sometimes? No, because you have the length of a chord is the length. I mean, it's very basic what I'm saying, but you get an eigenvalue which is the length of a chord. I'm sure that some people have made a graph vibrate or something before, but have you? I don't know what have you.
people do that. And it actually works. If you have a graph and you use the weights as length, it means the graph vibrates at the correct thing. No, I don't think this is related to that, but when you have the Laplace equation, then you have the heat equation. So the heat equation looks like this. Also, I'm solving this equation, and the heat equation is like that. And I'm pretty sure that if one should be able to make sense of the heat equation in an algebra, and that should be something interesting. Yeah. But again, this really depends.
Deformations, maybe?
Yeah, so I don't know. So the heat equation is like a simplification of things. No? So you start with something. So people do it to study K theory. No, it's not arbitrary. So you start with something and you let it evolve using the heat equation, and it becomes simpler. No, so it's related to the formations and to the generations of things.
Mm. Mm. Yeah, very, very interesting.
Any more questions, comments? Well, thank you again, Mariano, for the nice talk.
Very nice talk, Mariano.